So we're going to conduct a project. Hopefully it's not an experiment. To determine the speed of 22 caliber bullets. We assumed when we did the flash photography that the bullets were traveling at some rate, which was close to the speed of sound, right? But whether it's that or something else, we don't really know. You take my word for it that they travel roughly at 1,000 feet a second. How fast is that? Well, I think that would be kind of difficult to try to determine by watching one fly. Okay. You could say, well, what I could do is set up an obstruction here, a piece of paper, another piece of paper over there, and I know what the distance is. And I could put a gun over here and fire it, and then time how long it takes for the bullet to put a hole in this piece of paper as opposed to that one, and use a stopwatch. It wouldn't work very well, would it? Oh. However, a street camera might work. It has to have very good time resolution. It means it needs to be able to measure or display small increments in time. So the digital camera that I have won't work. I have a more sophisticated one, but even that doesn't work. And you'd have to go to a sort of military grade street camera in order to do what we're going to do with a camera that, again, is an improvisation, but improvisation is cheap, and it'll give us the information that we need. The camera is called, or looks sort of like this. Well, remember, a camera needs a slit of some kind and moving film. On this camera, the moving film is provided by the film being wrapped in a drum. Okay, those are the sprocket holes, and this drum can be spun. And out here there is a lens to form an image of whatever out there, and it's going to be the bullet. And we could assume, for example, that to begin with, we'll set up what is called a steady state experiment. Nothing is moving. So the drum is sitting there. Of course, this is in a light tight box, etc., etc. Oh, this has a circumference of 12 inches. That'll come into play shortly. And how is the film attached to it? Well, it's just wrapped around it, and a piece of tape, Scotch tape, or whatever, holds it down. So now out here, we're going to put our subject. And the subject, well, for the sake of argument, I'll use a couple of light bulbs. But we're not going to use light bulbs. We'll use something similar. But we can put one light bulb here, another light bulb here, and for the sake of convenience, we'll make this distance some known distance. What do you think that distance might be in order for it to be convenient later on, since we're measuring the speed of this bullet in feet per second? Oh man, my ESP worked. We'll make it 1 foot. Okay, so that'll be our known subject distance. Now that'll be reproduced on the film at some size. Okay. Now we probably want to put it, these are the sprockets. Okay. We probably want to put those two lamps, one here and another one there. Okay. So now they're just sitting there. If in the course of events the drum here turns, in that case these lamps, since they're just sitting there, are going to leave a streak on the film, right? And the streak is going to go from where to where? It's going to go from all the way around the drum, right? Because they're here, and then when the drum moves, so we'll have with two lines of density. This is the sort of very beginning of the slides that you saw earlier, right? Stationary lamps, moving recording material, lines that are parallel to each other, parallel to the time dimension. one thing we do know is that the distance from here to here, regardless of what is on the film, is going to be 1 foot. Right? If we move those further away, the distance between those two lines will shrink. Right? So in any case, now what we're going to do is we'll put a gun over here, and I'll aim it away from you.
Thanks, Andy.
So here's the gun, and the bullet is going to come out and fly around here, and we aim it so that it hits the lamps.
It's the lamps?
Well, yeah. Those lamps.
That's empty.
So anyway, we start the process going, this thing is moving, it's recording lines for the lamps that are turned on, and eventually, we fire the bullet flies here, boom, this one blows up, goes to the next one, boom, that one blows up, and the lamps disappear. But that's okay, they left what we needed already, okay, so they're disposable at that point. The one thing that is ensured by doing that is that the bullet is in the same plane as the lamps are. Because if it's not, in that case, your measurements are going to be off. So what happens? If we put enough light on here, so that the bullet, even at the speed that it's moving, reflects enough light back to the camera, it's going to be, the image will be here someplace, and because, let's say that this is moving this way, it's moving this way. Yeah, by the time it gets to this side, some film will have moved. And so you get a trace that might look like this. Right? What we can tell from this is this was lamp 1, this was lamp 2. The distance between them was a foot. Now we need to find out how much time elapsed between the time that the bullet was at one versus the other. And where is that information? Right here. We find where the intersection of that line is, of the bullet streak, is with that line. We drop it down here and we get some distance. Now that distance is equal to time. Right? If we know how fast the film is moving, if we know what our time base is. So if the time base is such that this distance stands for 1 second, in that case it took the bullet 1 second to travel 1 foot. So now we're going to say, well, we did come up with a convenient distance at the subject. What about a convenient time base? Well, the bullet is going to be moving at about 1,000 inches a second. So what might be a good time for it to travel 1 foot? Anybody?
A second?
How much?
1 second?
No. That'll be too long. The real bullet now.
1,000.
Yeah, about 1,000th of a second. So let me put the film horizontal here for the time being. We have our two 1 foot apart marks, and we're going to get a line over here. Here's the intersection of the bullet with one of those lamps. Here it is with the second one. And now, if you measure this distance, if this still is truly moving at 1,000 inches per second, then this dimension, if it's 1 inch, that's equal to 1/1000th of a second, right? Yeah. So it traveled 1 foot in 1,000th of a second. Velocity, change in distance divided by change in time, right? What's our change in distance or position? 1 foot, right? What's our change in time? Well, 1,000th of a second. What's the speed? Well, 1,000 inches. 1,000 feet per second. supposing that the bullet, okay, makes a trace like this. Is that bullet traveling faster or slower than this one?
Faster.
Excellent. If the line is like this, it's moving infinitely fast. Now, what happens at a different magnification? Supposing that these two lamps are closer together. That's not what I meant. Are closer to the camera. So the two lamps now, instead of being this far apart, could be this far apart. What will the line look like?
Should be the same. Slope should stay the same. Maybe.
The time remains the same. It takes the bullet the same time to go between the two lamps. So we want to make the time the same. So the bullet is going to be here at one,
Okay.
and then it'll be here at the other.
At that point.
So the slope is going to be steeper. The time is still 1,000th of a second. The distance is still a foot, but the slope of the line changes with magnification. We're going to get back to this. So now we say, okay, we know the two parameters. One is at the subject, 1 foot, and over here we want to film in this camera. It will be called a rotating drum streak camera. They have a lot to be said for them because they don't use an awful lot of expendable material. Only 12 inches. That's the circumference of this drum. Well, actually, a little more than 12 inches because you want to have a little overlap. So, 13, 14 inches, 15 inches. But anyway, we're interested in the circumference being 12 inches. Now, we have the capability of rotating this, and we adjust it by how fast the drum turns. So we want to turn this drum, 3D drawing over here. We want to adjust the rotation of this drum so that 1,000 inches of film go past, we'll put a slot in here. 1,000 inches of film go past that slot every second. That means that the film will be moving at 1,000 inches a second, right? How do we do that? Change the RPM of the drum. How do we determine what the RPM of the drum should be so that its surface is moving at 1,000 inches a second? I forget. So first of all, we're going to do what? We could approach this from the point of view that we're going to adjust RPM, but we might think about this, trying to think of a logical way of doing this, is as well, the neat thing here is that we want to go 1,000 inches a second. Yeah, this is figuring out. If we simply take what speed we want this to be and divide it by 12 inches per revolution, okay, we end up with revolutions per second, I believe. And if you do this, that something was weird.
Oh, that's right. You get a sense. Yeah, you get revolutions per second.
It's too few.
But then we just convert it to RPM.
Ah, that's where exactly. Very good. So we get revolutions per second, and this would be what? That'd be 10, a bit 9, a bit 8 something. Is that right?
No, that's not right.
Where's your iPhone? Calculator.
Alright.
Come on. 1,000 divided by 12. It's 80 something.
83.322.
80. 5,000 divided by 12 is 83. It's 80 something, that's right. 83 revolutions per second. Well, we want to go to, because this is calibrated in RPM, okay, we want to multiply this times 60 seconds per minute. And we end up with a RPM value of what?
5,000.
Hey, that's pretty nice.
Yeah.
5,000. Oh,
It's pretty sweet.
I like that. 5,000 RPM. So somehow or another, we managed to make this run at 5,000 RPM. And we'll get to that in a second. So when that is happening, the film is moving past 1,000 inches a second. 1 inch of film will be 1,000th of a second in time. We get our time base. We get our distance from the subject. Okay. Now, what next? How do we adjust the speed of this drum? There are many ways of doing it. We are going to use something that is near and dear, or used to be, to the hearts of anybody who works with engines, car engines. And how do they determine the RPM of the engine? Or what's the device that's used to do that?
Tachometer.
It's called a tachometer. We're going to use a phototachometer. A phototachometer measures interruptions of a light beam. So we'll attach to this shaft, we'll attach a vane like this, okay? And out here, we'll put a photocell. And back here, we'll put a lamp. It's not quite the way that we're going to do it, but you get the gist of the idea. We have a lamp, it goes to the cell, and this will interrupt the light beam. So the phototachometer says it's interrupting it so many times a second. And if it interrupts it 83.3 times, we know that the drum is turning 5,000 RPM. The tachometer itself is probably already calibrated in RPM, so we don't have to go from here to there. So, you know, the tachometer, this is going to be our measuring instrument. It's calibrated to National Bureau of Standards. And we're not going to question whether the tachometer is accurate or not. We just assume that it is. So, interrupt it 83 times a second. And, but I'm remembering now that the tachometer that we have is modified so that it will be suitable for the last project that we do this quarter. And for that, it needs to run slowly. And because if it ran at the rate at which we will need to run it, then the tachometer would go like this, the needle.
Mm-hmm.
And that's not good. You want it to go to the point and stay there. How do we do that? Anybody? What we do, increase the number of vanes. So now it reads 4 times every time it makes one turn. So the needle, instead of going, it goes. And if you want it to be more steady, you add more to it. And eventually it's going to say, well, I can't go down during the dark period, right? So this one is adjusted with a 4 cutoff. So in order to make this go to 5,000 RPM, our tachometer, phototachometer, is going to need to set to 20,000 RPM. When it's running at that, it's actually running at that. It would have no problem with just one. But because it's set up for the last week, I had to do this. All right. Now the other thing to consider is one of the questions that optional final had to do with a subject becoming its own shutter. Right? This is a prime example, because this bullet is moving. And if you were to just take a camera over here and open the shutter and have the bullet fly across, you'd never see it. The exposure time per unit area on the sensor is so small that it won't be recorded, unless you pour an awful lot of light on it. That's what we're going to do. I'm going to take a high-power electronic flash over here and light up the flight pen. We'll set off the electronic flash with a sound synchronizer. And I think I just found this. I made this maybe some years ago. and I forgot what it was. But luckily, on the back, I said, David Hazy Sound Sync. And it has, yeah. So maybe we'll use that one. It's probably something that you can buy at a grocery store for turning a light on and off, clapper thing, and that's probably what it is. So anyway, we fire a flash, and this will be fairly close to the flight path. And essentially what we're looking at is providing enough light so that during the time that the bullet moves its own length, it's high enough to cause an impression on the film. So we could say, well, what is the exposure time that the bullet is delivering? Well, we know something about the bullet, right? It's roughly 10 millimeters long, right? And something. How fast is it moving? Well, about 1,000 feet a second. Well, how many? Let's do that in millimeters. So you want to convert from a foot to millimeters. How many millimeters in a foot? This is the reason that satellite missed Mars.
25.4 times 12.
And what's that? Roughly speaking.
305.
305 or 300 millimeters, right?
Yeah.
So, but that's per foot. Now we want to go. We want to convert to 1,000 feet, not just 1 foot. So that's.
300,000.
So this is traveling. The bullet is traveling at 300,000 millimeters per second. That's the equivalent of 1,000 feet a second, right? I mean, roughly.
Yeah.
So that's the size of the bullet divided by 300,000 millimeters per second. So the exposure time is going to be what? Well, it's going to be, take 1 0 out of there, 1 0 out of there. Did I do it right?
Yeah. 10,000. Yeah, 30,000.
1/30,000th of a second. So we need to provide enough light for that. That is going to be, we're not going to actually figure that one out. But you could figure out how many foot candles that is using that Sunny 16 equation, right? And knowing something about the film speed. But in our case, all we want is some kind of a trace. So we overexpose it a little, that's fine. Overexpose it, underexpose it a little, that's probably okay too. So now let's see what else. As far as this flashes, what we want is a light source that is on all the time that the bullet moves across the 1 foot dimension. Well, how long does it take it to move across? Well, roughly 1,000th of a second, right? That's what we figured out. Oh, come on, Andy. Roughly. That's how long it takes. So the light only needs to be on for 1,000th of a second, right? However, if you take a look at a studio flash, which is what we'll use, we talked about flashes before, They have a pretty good rise time, and then they have a long decay time. Studio flashes give you lots of power, but are fairly long duration. And if you time one of those, go from here to here, that might be as long as 100th of a second, maybe even longer. So as long as we fire the electronic flash before the bullet gets to the first lamp, the duration of the electronic flash is going to be long enough to illuminate the flight path of the bullet and give us a lot of light. The problem with electronic flash going off over here, that if you have a background here, which is, let's say, 18% gray, you're lighting this bullet up that's giving an exposure time of about 300,000th of a second. But the film over here that's rolling around here is exposed a number of times in 1 second, or even 100th of a second. Well, in 100th it's only exposed 1 time. Well, maybe that's why it worked. But anyway, we need to worry about the fact that we have the bullet here, but then we have the background here that's also reflecting light. Well, that's no good, because we're going to get noise from the background, right? So we're going to make this a black hole. Black holes are great. They don't exist, except out there somewhere. But from an imaging point of view, having an absolute absorber. It's very useful, especially when you're doing flare studies. You want a subject, when you're doing flare studies, a hole that light goes into and nothing comes out. And there are many ways of doing that. Well, I'm not sure that any one of them is 100%, but there are some that are better than others. So we want to make sure this is as good a black as we can get. Keep the light off of it, because we want the light from the bullet to impress on the film, not the light from the background. And the bullet is only going to be there for this long on any given spot. The background is going to be there all the time that the light, the flash is producing light. So to separate signal from noise, use a good black background. And oh wow, and what else? Well, I think that's about it. I do this a lot faster than I thought I would. So that gives me a chance to ask the oft-asked question. Are there any questions?
We just need to
You
bring
will need, yep.
film.
What?
We just need to bring
Just need to bring film, and just about any film will work.
black and white.
Sort of, kind of. Yeah, if you want to do the processing, black and white film works pretty good.
Right.
I guess you can send it out for processing, but it's pretty expensive.
Yeah.
It's more expensive than color. So, color film will work, black and white film will work.
We need our hearing protection and eye protection.
Hearing and eye protection, that's correct. And you don't need a camera though. I will provide the camera. And again, it's going to be a process of, there's only one camera.
You can provide the rifle.
I will provide the rifle.
Just, she got excited there.
Right, no, I will do that. And
It's allowed, isn't it?
anything else that I can think of.
There's something about, that's not really.
One roll per group.
Yeah, in fact, you may not even need a whole roll, but I'm not sure what you're going to do with a partial one. The only problem is that this camera, being a home-built improvised system, and the fact that you are attaching the film to the drum with a piece of tape, and you're spinning this drum at 5,000 RPM, that'll tend to blow the film off of the drum if it's not attached properly. And so in that case, you might need
That's better.
2 pieces of film. But when you figure it, you only need 15 inches. Yeah.
I mean, I have 10 rolls of Kodak Max that expired back in 1990 that I'd be more than happy to donate. So I have nothing else to use.
There you guys.
So
Yeah, except that it's black and white.
no, it's Kodak Max.
Oh, Max, what's that, an C41?
Yeah, it's really crappy C41 film. So if people want to use it, they're welcome to. I'll just bring.
Bring a few rolls.
Yeah.
Or you can bring your own.
My freezer's full.
So we're going to photograph 2 bullets, a short and a long. And we're going to do it by firing one, and then loading the gun again, and then firing the second one on the same piece of film. You can expect to see 2 bullet traces. Right? And the result might look like this. It's the edge of the film. Here's your 2 lines that indicate 1 foot, and you'll have one line like this, and you'll have another one like this, or maybe you'd have another one like this. Or oops, yeah, or you could have something like this. Highly unlikely, but why is this unlikely?
Because you have 15 inches of film where it could go anywhere on that. It's the fact that you're getting this exact spot.
Yeah, especially over here, they're all at the same time.
When it's moving at
Right.
5,000.
So it's on multiple, so this thing turns around a multiple number of times in between the 2 shots. So you really can't tell when the second one was fired. All you can tell is how fast it was moving. And again, the lower the slope, the slower it moves.
Cool.
And if you have any questions about how to analyze this, you can ask me again later. So that's it. By the way, next week we're going to use film again. 400 speed film, 35 millimeter, and you'll need probably at least a 24 exposure roll. Take care. Have a good week. Have a good day. Good evening.
So how do the
see
film
you
actually
tomorrow.
attach as drawn? Like how do we load it?
I'll show you that tomorrow.
Okay.
Would a different speed film work? Would a different speed film work?
With a different speed film work?
Yeah, I have a bunch of 100, but
That'll work.
okay.
I think it'll work.
With rear facing seats.
Whatever.
It used to be nice when we had it's called a Versamax,
Gonna vomit, it'll be on the
a
back.
Kodak
Easier to clean.
black and white processor that you could feed the film in, and that would come processed. We don't no longer have that. The neat thing about that was you could do a test exposure, and then you take it to the machine, and then look at it, and then you could see if 100 speed film was okay or not. Now we're just going to have to kind of guess.
I can bring a variety of speeds.
Okay.
I've got 100 and 800 laying around too.
What color or black and white?
Both.
Okay.
I've got
The reason I suggested color is because, like the young lady over there, she says, "Well, what's film? Where do I buy it?" And it's becoming more and more like that.
Let's see.
So
I've got a big stash I've been collecting over the years. So
you,
my roommates, like every time I move, my roommates are like, "What does this all do in the refrigerator?"
you can bring it and share it. That'll be fine. Maybe nobody will need it, but it's nice if you don't.